A rational expression, just another way to say a fraction that involves expressions or polynomials. Okay. The first thing that we're going to talk about involving rational expressions, because they have division by variables oftentimes, is the domain. Okay. You have to be aware of domain restrictions. Okay. If you guys recall, domain is what? What does it mean? So if I give you an expression, so if I told you you have this expression right here, is there any restriction to the values you can put in for x on this? Is there anything about this polynomial form here that restricts the value of x? No. There's nothing for it. So when you identify your domain for something like this, especially any polynomial form, the domain is simply all real numbers. Now, the domain may be represented with this symbol that stands for real numbers. It might also be represented in interval notation, if you guys recall that. The interval notation for all real numbers is negative infinity is our lower limit, all the way to our upper limit of positive infinity. Okay, so it may be expressed in either of these ways. You need to be aware of both. Okay. Now, as far as restrictions on the domain, there are some ways that restrictions can be incorporated. Okay, one is by a formula. Okay, so you have this formula. It should be familiar to everybody. This is the formula for the area of a circle. Okay, and because it's a known formula of a geometric figure, is there any restriction on the variable for that? If you have a circle, what do you know about its radius? It has to exist, right? So in order for it to exist, what do we know about r? R has to be greater than 0. It can't be negative, it can't be 0, it has to exist. And so if we incorporated that in the interval notation, what would our lower limit be? The lowest number, 0, and our upper limit would extend all the way to infinity. Okay. Now, we may also get other restrictions based on things we know about the expression. So an even indexed root, if I gave you this expression under an even indexed root, again, what do you know has to be true about this whole expression? You can only take an even indexed root of a non-negative number. So in order to guarantee this expression x plus 4 is non-negative, you would have to take that expression, x plus 4, set it greater than or equal to 0, and that's going to give you your restriction. So if you isolate the x here, subtract a 4 from both sides, you would get x is greater than or equal to negative 4. And so here is your restriction, x greater than or equal to negative 4 in inequality form. The interval notation form of this gives us a lower limit of negative 4 and upper limit of infinity. You can never reach infinity. And what symbol do we need around the negative 4? It's included in the set, so it would be a bracket. Now, all of these restrictions here are restrictions that we've already talked about. And we've never specifically said how to express them, but we've dealt with all of these before. The new set of expressions that we're going to introduce in this chapter are rational or fractional expressions. And so if I gave you a rational expression, okay, so this is a negative here. So if I give you this rational expression, what extra restriction applies to a fraction? You can never have a 0 in the denominator, right? Okay, so what you'll need to do on this type of expression is you're going to identify what factors would give you a 0 in the denominator. Set those factors equal to 0. And those are going to be your restricted values. So for domain, oftentimes, you're looking for restrictions. So in this particular case, does it matter what's on the top? Not really. Not when you're just finding domain. So you're going to look at the bottom. Can you, so the top can stay exactly as it is, what would be the factored form of the denominator? It's a difference of squares, so it would be x plus 2, x minus 2. And so what two values of x would give you a 0 or division by 0 in your rational expression? Negative 2 and positive 2. So your domain, in this case, is all real numbers. X cannot equal plus or minus 2. Okay, so it's easier to express this as a restriction rather than the set. So all of these up here were expressed as the sets. Here we're expressing them as everything with the exception of whatever the restricted values are. We can still express this using interval notation. It's a bit more complex. Okay, so we want all the values from negative infinity to infinity, except for 2 and negative 2. Okay? So when we look at these, what we have is from negative infinity to negative 2. Now we have to go from negative 2 to 2. Let me leave some more room here. And we also have to go from 2 to infinity. Since we're dealing with multiple sets of intervals, we join them with the union of sets symbol. Okay. So, somewhat complicated way to express the same thing, but you do need to be aware that this may be the form that I'm asking you to identify. Okay. So does everybody see how this interval notation represents the same thing as this inequality form or this restricted value? It goes from negative infinity to negative 2, does not include negative 2, still does not include negative 2, but goes from that all the way to the value 2, doesn't include the 2, but it again extends from that value all the way to infinity. And so this is the way that you can express those restrictions. Okay. All right, if you look at sample problem 1 on page 30, all right, for the first example, what would the domain be for this? The domain is all real numbers except for 2. That would be the only value that gives you 0 in the denominator. What about the second example? To find the domain, we have an even index radical, so what do we have to do with that expression underneath? We have to take that expression, set it greater than or equal to 0, because it can be a 0, it can't be a negative. And so when we solve simply for x, we get all real numbers as long as x is greater than or equal to what? Negative 2. Again, what we did is subtract a 2 from both sides. And simple algebra. We haven't talked about equation or inequality solving, but I'm assuming you guys can do the simple math involved in these. And then finally, the last example. The domain restriction is going to be all real numbers except for what values are restricted here. Are there any restricted values? What value of x could possibly make the denominator 0? Nothing, right? So your answer is just all real numbers. Okay, remember, there's no factor patterns for the sum of squares. Notice we did the difference of squares. We did the sum and difference of cubes, but there's no sum of squares pattern. Sum of squares are what's called irreducible across the reals. You can factor it in the complex number system or using imaginary numbers, which you guys will probably do in precal. But as far as the real number system, it's irreducible, can't be factored any further.